Today is a very, very sad and difficult day. Oh yeah, oh yeah. It is time for us to say goodbye to a very dear and special friend. I realize that it will be hard for many of you to say goodbye to our dear friend Sigma, and I want you to know that I feel very same in my heart as well. But together, we will try to get through this, not because we have lost Sigma, but in spite of it. So let's talk now about what happens if you don't have Sigma. True story. About 90 years ago, a guy named Gossett works in Ireland for the Guinness Brewery Company. His job is to test what makes a better beer. So he would draw nice normal distribution, because that's what we always do. And then for his standard error, he would use sigma over the square root of n, because that's what everybody did. Now, he didn't have sigma. He had to use what his data said was a good estimate for the standard deviation. That's S. So he wasn't really using sigma over the square root of n. What he was actually using was S over the square root of n. But he still used this picture because that's what everybody did. Well, he would taste test the beer and then bicycle home. And the next day he would taste test beer, bicycle home. As you can imagine, he needed small sample sizes. With a small sample size, this standard deviation here is not that close to that standard deviation there. And he noticed his data didn't always fit in this nice picture here. He had extra error. Like that much extra error being introduced into his model. Why? This error right there is from S not being perfect. So he's using S instead of sigma, and that is not a perfect estimate of sigma, and so there's extra error. So his distribution looked kind of more like that. Just a little fatter. Being fatter means it was a little shorter as well, but this extra error came from having to use S. And he realized this isn't exactly a normal shape. It's close. It looks so close I can't draw the difference very well. But this is a different shape. And he went to the Guinness Brewery and he said, I have developed a new statistical distribution. It's a good way to handle if you're using S instead of sigma. And they said, that's nice, but we don't want you to publish your results, because if you publish your results, then our competitors are going to copy that, and then we'll lose our advantage. He said, please, I promise I'll print under a different name. They said, okay, you can either print and tell people your name is student or pupil. So he picked student. So this is called student's t distribution. And now we're ready to start talking about using the t distribution, whereas before we were always using the z distribution. What makes the t different? Well, it's got about the same bell-type shape. It's still centered over mu, that true parameter. The only difference between t and z is it's a little fatter. Why is it fatter? Because it's not perfect. And that sentence alone should cause years of therapy for the t distribution. So this extra error here comes from S not being perfect, but as you get more and more data, what will happen to that error? As you get more and more data, this S will start to look more like sigma. In other words, you'll have a good estimate. What that means is this error can disappear as your sample size gets larger. So the shape of the t distribution is not always the same shape. It depends on what your sample size is. The z doesn't care. The z is just the z. It's a bell curve. There's no differences. But the t distribution will change as you get more and more data. So we use what's called degrees of freedom. Degrees of freedom is a way to talk about what is the shape of that t distribution relative to our sample size. Here's how you calculate degrees of freedom. And this is just, I want you to have an idea. If you knew what the data added up to, if you knew the average before you started, how much data would still be random? If I told you you were going to do a survey and you were going to get an average of 17, would that tell you what the first person is going to say? No, the first person could still say anything. The second, third, fourth, you don't know what they are going to say. But the very last person, you could calculate what their answer would be by taking the average and figuring out what number you would need to get that average based on all the other data. So if we have degrees of freedom here, it's going to be n minus 1. What is that n minus 1? If you already knew the sum, then n minus 1 data points would be random, but that last nth data point, you could just subtract it from all the others from the sum, and you would know it. Okay? So when I write the t, I often put a little tiny n minus 1. N minus 1. Does that show up on the video? N minus 1. Yeah, I can see it there. That reminds us that the shape of the t distribution depends on our sample size. Here's another place where that n minus 1 showed up. Do you remember when we calculated s, the equation that we used? We used s equals square root of, and then we added up each of the data points minus the mean squared. Remember this? This was weeks ago. Divided by n minus 1. There's that degrees of freedom showing up again. If I already know the average, how much of this data is random? N minus 1 for degrees of freedom. So what does that mean? That means when we look at the t-table, we need to check our degrees of freedom first. And that means you're going to have a t-table for if you have 2 degrees of freedom. There is a different t-table for if you have 3 degrees of freedom. And a different t-table if you have 4 degrees of freedom. And a different t-table for 5 degrees of freedom. So can you imagine walking into the test? Here's your t-tables. Boom! You have to have all these t-tables. No, that's not the way we're going to do it. Let me show you how the t-table really works. Okay, so here's what our z-table looked like. We have the positive and negative z-tables. Here's what the t-table looks like. Okay? Now notice over here is our degrees of freedom. When we say degrees of freedom, this is one t-table. It's the t-table for what you would use if you had 1 degree of freedom. This is a different t-table. This is the t-table for when you have 2 degrees of freedom. Because degrees of freedom are n minus 1, if you had 2 degrees of freedom, that means you had 3 data points. Later, as we get into more complicated types of analyses, there will be more complicated equations on how to calculate that degree of freedom. So if we had 11 data points, we would have 10 degrees of freedom. This would be the t-table that we would look at. Okay? Notice that we only have a few values in this t-table. For the z-table, we had tons of values. And now we've got to work with something a little less. Here is what the tail probability is. And that's going to be hard to understand until I draw a picture. But if you had 10 degrees of freedom and your t-score was 2, so somewhere right in between here, you would know on your picture that you had somewhere between 2.5% to 5% in that tail. And that's going to be confusing, but let me show you an example, and I think that'll make it easier to understand. All right, here's our scenario. We are going to test if the average weight of a 1/3 pound Whopper, that's the name, it's called a 1/3 pound Whopper, but is it really 1/3 pounds on average? Okay? No 2 Whoppers are ever going to be exactly the same down to the atom, so there is some variability. Okay? So we select 10 Whoppers, we get an average of 0.37 pounds, and our standard deviation is 0.05. Here's a big difference, and you're expected to pick up on this. This 0.05 comes out of a sample of 10 Whoppers. So this is not the true sigma. This is an S. Because it's an S, we're going to use a T. If it had been sigma, we could use the Z. If it had said, we want to test the weight of a Whopper, assume sigma equals 0.05, now we're going to test 10 Whoppers and this is our average, that's different because then this 0.05 wasn't coming from a sample, it was just assume we magically know this. Okay? But we're not doing that anymore. This is very realistic. You could calculate this if you had a bunch of data. In fact, we'll have an example where we go through that. And we're going to test with alpha equals 0.05. Notice we still need normality. Okay? The fact that we're using a T is because we started with a normal and now we're estimating sigma. So you do have to have normality with a sample size of only 10. Let's go through this. Okay? What is my null hypothesis? We're testing if the average is 1/3. When I read this, I see mu equals 1/3. Is there an equal sign in that? Yeah, there is. So that's my null. Null mu equals 1/3. Alternative would be the opposite. It does not equal 1/3. Alpha, it already told us, Alpha is 0.05. Okay, now, this is the part that's different. I'm not going to write Z, I'm going to write T. What are my degrees of freedom? I had 10 whoppers, so my degrees of freedom is 10 minus 1, that's 9. I'm just writing that 9 to remind myself where I need to look on that table. And now it goes just the same way it did before. Here's the average we got, 0.37. Minus, what did we think we were going to get? The answer is 1/3. Divided by, standard deviation is 0.05. Divided by the square root of n. Our n is 10. So this should not feel like a new equation. It's one slight change because we're using s instead of sigma. What does this give us? 0.37 minus 1/3 divided by 0.05 over the square root of 10. And we get 2.34. 2.34. Now, remember I need a picture. Picture helps me not mess up. Okay? We were here at 1/3, but our data was a little up above that, right here. And when we looked, oh, we haven't looked it up yet. Let's go find out what that area is. Here is my t-tables, plural, because there's many of them. This is the specific t-table I'm interested in, 9 degrees of freedom. The t-score that I got was 2.34. Let's see, this is 2.2, this is 2.39, so it's somewhere in between there. With the z-table, I could usually find my z-score without a problem, but now I only know that it's somewhere between these two. So now I look up here, here's the area, somewhere between 2% and 2.5%, somewhere between 0.02 and 0.025. Let's draw that on the picture and see how it looks. So if this was where my t-score landed, my 2.34, I don't think I drew my picture very well. If that's a standard deviation, it should be out there a little further. 2.34. And this little tiny area right there, that's what the t-table tells me. It's different than the z. The z always told you from here to the left. Now with the t-table, it's from here to whatever is the small piece. Does this look like about 2%? If I'm any sort of an artist, it will. So this is somewhere between 2% to maybe 2.5%, somewhere in that range. Now, we have a two-tailed test. So this is not my p-value. I need to also add the same amount of area over there. Well, how much is this area? If this is between 2 to 2.5%, this side is going to be 0.02 to 0.025 as well. So what's the smallest that my p-value could be? My p-value has to be between, if this is as small as it could be, that would be 2%, and this is as small as it could be, 2%. I add those together, I would get 4%. So my p-value is somewhere between 4%. What's the biggest it could be? Well, if it was 2.5, and here it was 2.5, that would give me 5%. So it's somewhere between 4% and 5%. Okay? So I don't know exactly what my p-value is. Maybe it's 0.042. Maybe it's 0.048. Well, I don't have to know specifically because I have this alpha here. And I know that the p-value has to be less than 0.05. 0.05 is my alpha. So if my p-value is less than 0.05, that tells me I am smaller than alpha, and therefore I'm going to reject. Reject. If I reject, what am I going to conclude? Well, I rejected that the average is 1/3. What have we shown about Burger King? Their 1/3 Whopper really isn't. So we have proof. We have proof the 1/3 Whopper is not 1/3 on average. Except I'm running out of chalk here. 1/3 on average. Average. So what was different from what we've done before? two big keys. First, we noticed that this standard deviation was not the true sigma, it came out of a sample. Secondly, because this was S instead of sigma, we used a T, which was a slightly different table. It made us get a range for the p-value instead of an actual number, and then here, everything else will float the same. Now, in WebAssign, when you're doing this homework, because we're going to switch between old problems that use Z and the new problems that use T, sometimes WebAssign wants you to put in a range, and sometimes WebAssign wants you to put in a value. So you're going to find on old questions that are Z, it'll still ask for a range, even though you don't need that. And what it'll say is select true. And when you see select true, just pull up in the menu, you'll see true, click on it, and when you try those problems, in fact, maybe I'll show you an example. But we'll do that on the next video because this one's pretty long, and I'll explain what I mean.